Okay, I want to talk about Newton's laws because I noticed when I was checking through the labs that we're having some misunderstandings about Newton's third law. All right, so this is the part on the simulation where we had blue people and red people. So if I were to draw a free body diagram for this cart, there is going to be a force this way, which is our red people. I'm going to put force of red people on the cart. And then there would be a force this way, and this is the force of the blue people on the cart. Now notice, both of these forces are acting on the cart. Now, because these two are the same amount, the force of the blue people on the cart is equal to the force of the red people on the cart, then that means this is balanced, and my net force is 0. And according to Newton's second law, F net equals ma. If my net force is 0, then my acceleration is 0. So when I asked you what law applied to this one, that would be Newton's second law. You could also say it was Newton's first law. Now, if in the case that the blue people pull harder, so this is when we increased this one, then in that case, the blue people were pulling more than the red people, so my net force was not 0, and it was in fact 150 newtons to the left. So that means since we have a net force, according to Newton's second law, I would have an acceleration to the left. Okay, now here's where things fall apart. When we talk about Newton's third law. Okay, and I don't really like the for every action there is an equal and opposite reaction, because these two forces, these action-reaction forces, or I call them Newton's third law companion forces, these occur simultaneously. And there have to be two objects. Okay? When we look here, there's one object. That was the cart. And I had two different forces that acted on the cart. Okay? If I want to talk about Newton's third law companion forces, okay, this is the force of the red people on the cart. Now, if I would draw a free body diagram of the red people, these are my red people, there would be a force acting on the red people, and this would be the force of the cart on the red people. Okay, now notice, red people on the cart, cart on the red people. These two forces are equal and opposite. Okay, those are the Newton's third law companion forces, but we're talking about two different objects. We're talking about the cart and we're talking about people. So there are two different free body diagrams, and those Newton's third law companion forces are always on different diagrams. Okay, in this case, I had two forces acting on the same object, both acting on the cart, but two different forces. Okay, those are not Newton's third law companion forces. If we think those are Newton's third law companion forces, then nothing would ever move because they would always be equal and opposite. Okay, but in this case, they did move because the blue people were more than the red people. Okay, so in order to be Newton's third law companion forces, those have to be acting simultaneous, and they have to be two different objects. The cart on the red people and the red people on the cart. And you can tell these are the same two things, just reversed. Another example is, let's say I have a hand, and I'm going to smack somebody in the face. Okay, so here's his face, his little nose. Okay, so if I smack somebody in the face, here is the picture of the free body diagram of the face. I would have the force of the hand on the face. On a separate diagram, here's my hand, I would have a force of the head or the face on my hand. Okay, so once again, I have two different pictures here, and I have hand on face, face on hand. Okay, these two are Newton's third law companion forces. So when you think about Newton's third law, in order to get it right, reaction. Newton's third law says that for every force of object 1 acting on object 2, there is an equal force of object 2 acting on object 1 in the opposite direction. Okay, that is Newton's third law. Okay, I have one force acting on another object. That same object exerts a force back on the first object, and they are equal and opposite. Okay, and I think you'll get it right in your head that way if you think about that instead of the action reaction.